Hi guys, can you guys hear me?
Yes.
Okay. All right. So here is the information regarding exam 3 next week. So exam 3 is going to be April 26th from 1 p.m. to 2:15 p.m. The exam is going to be 75 minutes long. Okay. So 1 hour 15 minutes. And the exam is going to cover little bit of the later portion of chapter 17 and then entire chapter 19 and entire chapter 20. Okay, sometime tomorrow I will post the study guide. The study guide will list the detailed topics that will be covered in the exam. Okay, the exam is going to be multiple choice questions, about 33 to 35 multiple choice questions, and there will be no extra credit or no makeup exam for this time. Okay, because we're heading towards the end of the semester and I physically don't have time to grade those materials. Okay, so try your best, put all the um, try the best you can for this exam. And if you want to schedule an office hour before the exam to clear up some of the parts that you are still struggling, then feel free to schedule an office hour with me. If I have too many students scheduling an office hour with me, then what I'm going to do is I'm going to hold a study session where multiple people can join the office hour at the same time, and we can go over some of the topics that students still struggle with. Okay, so that's that. And as for the lockdown browser, again, lockdown browser is going to be used. Make sure your face is not away from the camera. Okay, and then make sure you ensure that you have quiet environment to take the exam. It is your full responsibility to prepare an environment where you can focus on the exam and take the exam. So make sure you have proper location to take the exam. If you have to reschedule the exam due to medical emergency, you need to provide me a doctor's note so I can keep it as a record. Okay. If you need to reschedule due to athletic competition or due to some other religious reasons, then please contact me ASAP so I can reschedule your exam. Other than that, if you miss your exam due to work, if you're trying to reschedule your exam due to work, then I can't reschedule your exam just because of your work schedule. Okay, you are you are enrolled in live web-based class. That means you agreed to dedicate Tuesday, Thursday, 1 p.m. to 15 p.m. For this class. Okay, so your attendance, your um, dedication for Tuesday, Thursday, 1 p.m. to 15 p.m. for this class is mandatory. Okay, it is not optional. Okay, so if you have work, you need to ask for an excuse. Okay, or and if you need quiet environment to take the exam, and if you really don't want to take it in the library, in that case, I can schedule exam time a little bit earlier than usual, or just slightly later than the regular exam time, but I cannot let you take the exam some other day than next Tuesday. Any questions related to exam 3? All right, so if there's no other questions, I'm going to finish up chapter 20. Okay, again,
Uh,
uh-huh.
I'm sorry. In regards to um test test the test that's coming up, what would you say is probably the area that students have the most difficulty on this test?
Probably the electrochemistry part. So what I'm going to do is we only have a little bit of remaining chapter 20 left over, so I'm going to quickly cover the remaining of chapter 20, and then I will try to go back to the earlier portion of this electrochemistry chapter and go over some of the parts that you guys might think it's challenging. Okay, like voltaic cells, or how to, what others? Because there will be a lot of questions about the voltaic cells, and I really want you guys to have clear understanding of it. I'll go over the voltaic cells one more time, and then I will go over the reduction potentials one more time. During last class, I found out that some of the students are still confused with the reduction potentials concept, so I'm going to go over that again. And then the relationship between Gibbs energy and the cell potential, equilibrium constant. I'm going to go over that one more time. Yeah, so those topics I will go over one more time today. Okay, and the exam will consist mostly chapter 19 and chapter 20. Okay, so there will only be a little bit of chapter 17, those very little later portions of chapter 17 going to be included in the exam. So doesn't mean that you don't have to study a later portion of chapter 17. It's just the portion of the exam is going to be heavily based on chapter 19 and chapter 20. Okay. Any other questions? Yeah.
When would we know, like, if you're gonna schedule a study session?
Study session. So I don't need to schedule a study session because I don't have to log on to the WebEx waiting for students when nobody joins, right? I'm just going to schedule one just in case if a lot of students are scheduling office hour with me over the weekend, then I will announce it on Web Campus. Hey, there are so many people requesting for office hour. Let's have a group session on Sunday, group session on Monday, something like that. Okay, but unless I receive tons of requests for office hour, I'm not going to hold any study session. Okay, so if you want to have an office hour, you can go ahead and schedule with me. If you have a specific question about sample problem sets, or if you want to clear up some of the concepts for the exam 3 material, then you can schedule an office hour with me. Yeah, I only have one office hour scheduled so far, so I'm not sure. Okay, but I'll put the announcement on Web Campus if there's any group study session going on. Okay. All right, can you guys see the screen that I'm sharing?
No.
Okay, how about now?
I can see it now.
Okay. All right, concentration cell is where we stopped last week. Not last week, on Tuesday. So basically, concentration cell. Concentration cell is a voltaic cell that are voltaic cells that are designed using the same species in both half cells, but through variations of the concentrations. Okay, so let's try some sample exercises related to the concentration cell. A voltaic cell is constructed with two hydrogen electrodes. Electrode 1 has hydrogen gas, partial pressure of hydrogen gas given as 1 atmospheric pressure, and an unknown concentration of proton dissolved in the water. Okay, electrode 2 is a standard hydrogen electrode. Again, the hydrogen gas partial pressure is given as 1 atmospheric pressure. The proton concentration in this electrode 2 is 1 molar. At 298 Kelvin, the measured cell potential is 0.211 volts, and the electrical current is observed to flow from electrode 1 through electrode circuit to electrode 2. What is the pH of the solution at electrode 1? Okay, so the question says electrical current is flowing from electrode 1 to electrode 2. Therefore, we know that electrode 1 is the anode and electrode 2 is the cathode, right? So let's write out the reaction occurring at the anode. So anode is an oxidation site. So we know that at this location, hydrogen gas will be oxidized into proton. Okay. For the electrode 2 is the cathode, the reduction site. Okay, so we know that the proton will gain electrons to generate hydrogen gas. Okay. Now that we have figured out the half reactions, let's write the overall reaction. Okay, so the overall reaction is going to be okay. And I did not include hydrogen gas because it is specifically listed here that equal hydrogen gas of equal partial pressure is existing in both sides. So I'm not going to include that in the overall equation. But we know for sure that concentration of proton is unknown at the electrode 1. Concentration of proton at electrode 2 is 1 molar. Okay, so and then it also says that it's a concentration cell. So we know for sure that the proton concentration at the anode and cathode are totally different. Okay, so the concentration are different at the anode versus cathode. Okay, so let's try out the reaction quotient. The reaction quotient will be, I'm going to denote this as electrode 1 and then electrode 2. Okay, so the reaction quotient is going to be proton concentration at the electrode 2 raised to the power of 2 because we have coefficient of 2, okay, divided by proton concentration at electrode 1 raised to the power of 2 again. Okay, and we know that the proton concentration at the electrode 1 is 1 molar. Okay. Oh, I'm sorry. My mistake. This is a proton concentration at electrode 1. Two. Okay. 1 and 2. So reaction quotient is just basically proton concentration at electrode 2 squared. Okay, so now that we have reaction quotient figured out, let's before we so we have the reaction quotient ready. We're going to use the Nernst equation to find the numerical value of this reaction quotient. Okay, so the Nernst equation is log Q. Okay, and what do we know about this standard cell potential? Because we have same substance on both anode and cathode, for concentration cell, the standard cell potential is always going to be 0. Okay, so we know that this is 0. And then the number of electron transferred during this process is 2 log Q. Okay, and then the cell potential here is given as 0.211 volts. Okay, so if we solve for Q, I'm not going to go over the detailed math over here. The math is going to be pretty simple. The reaction quotient Q from this Nernst equation is found to be 7.4 times 10 to the negative 8. Okay, so what we know is that the proton concentration that we're curious of is equal to reaction quotient Q, which is equal to this value. Oh, I'm so sorry. Okay. And if we solve for the proton concentration, we have, if we square root of 7.4 times 10 to the negative 8, we get 2.7 times 10 to the negative 4. Now that we have proton concentration, we can easily find the pH of the solution at the electrode 1, which is basically negative log of this proton concentration. Which equals to 3.57. Okay. So that's that for the concentration cell. So for concentration cell, key things to note is that the standard cell potential is going to be 0. Why did I put equal here? Okay, 0. And then if you are asked to find a concentration of reactant side or product side, you just have to find the sulfur Q, okay, reaction quotient, and then that's about it. Okay, so nothing new, nothing difficult, just some of the concepts are different for a concentration cell.
Professor?
Yeah.
I'm confused on the part where E naught is equal to 0. How do I know?
Okay, so how do you find the standard cell potential? The reduction potential at the cathode minus reduction potential at the anode, correct? Do you recall that?
Yes.
Okay, all right, so then what is the reduction potential for this? It's 0. Reduction potential for this is 0. Why? Because we discussed in, let me know if the screen freezes, okay? So as we learned here that the scientists use reduction potential of hydrogen as a baseline, right? They gave the reduction potential of hydrogen a value of 0. Do you recall this slide over here?
Okay.
Yeah. So the reduction potential for hydrogen is 0, and you have hydrogen reactions on both sides. This is a concentration cell. You have hydrogen on both anode and cathode, right? So the reduction potential for cathode and anode will both be 0. Does that make sense? So then the standard cell potential is basically reduction potential at the cathode minus anode. So 0 minus 0 is 0, right?
Right.
Yeah. So
sorry. Do you have to have hydrogen on both sides of the equation for it to be equal to 0, or as long as you have hydrogen by itself?
this is a reduction potential. How likely hydrogen will gain electron? It's calculating that potential.
Yeah.
Does that make sense?
Yeah, I was just saying that if I have different elements in that equation as well, would it?
If you have different element, you will have different value of reduction potential. But then the if you subtract same number, then it's going to be 0 as well.
Okay, I see.
Yeah, because for a concentration cell, you will have same substance on both sides, right?
Right.
Yeah.
Okay, thank you.
Professor?
Yeah.
How did you get the 0.0592?
Nernst equation.
Okay, thank you.
All right, so that's that. And before wrapping up this chapter, we will be learning about some practical applications of electrochemistry, such as making different types of batteries, preventing corrosion, and lastly, we'll learn briefly about something called the process called electrolysis. Okay, and as for the batteries, the voltaic cells that we have been learning throughout this chapter are how batteries are operating. So so far we've been learning about the chemical reactions that occur within a battery. Okay, so through those redox reactions within the voltaic cells, within the batteries contain electrochemical power to use for flashlight or clocks or your calculator or even electric cars. Okay, so any batteries that cannot be recharged are called primary cells. Any batteries that you can recharge, okay, those are called secondary cells. Here are some examples of batteries. Okay, so lead acid batteries are basically batteries in your car, not electric car, but gasoline car. So this battery is used to kickstart off your car. Okay, so it doesn't provide enough power to run your car entirely, but it will provide enough energy to kickstart off your car, and that's made out of lead acid battery. The cathode of this battery has lead dioxide. Okay, and then the anode of this is solid. The anode of this the battery has lead solid, and then H2SO4. And then both are submerged in sulfuric acid. So you don't have to know the detailed chemical equation for this battery type, but since all of them, but what you have to, the key things for this lead acid battery is that since all of the major reactants and products are solids, the reaction quotient is going to be 1. Okay, so the reaction quotient, the product concentration divided by reactant concentration, that reaction quotient is going to be 1. So the relative amount of reactants and products have pretty much no effect on the voltage of this lead acid battery. Okay, however, that's the good point, but then the downside is that it's made out of heavy lead. Lead is very heavy. And then sulfuric acid, the solution they use to submerge these materials, that's pretty toxic biohazard. Okay, so you need the proper disposal of this lead acid battery. Okay, so when does the lead acid battery stops operating? The voltaic cell, okay, through this reaction, it will produce lead sulfate as a byproduct. Okay, and this should be converted back to the original electrolyte, and the battery keeps going up, operate again and again, going again and again, and you can recycle it, right? But eventually there will come to a point where your battery's completely dead. You can't recharge your battery anymore. And that's because this lead sulfate loses capacity to go back to the original reactant state because of the crystallization of this lead sulfate. In that case, there will no more, the battery is not rechargeable anymore. It will die, and then your battery's dead. At that point, you need to change your car battery. Okay, so that's the lead acid battery. Alkaline batteries are the type of primary battery. Primary battery means you cannot recharge it, right? So type of primary battery which gets energy from reaction between zinc and manganese dioxide. Okay, alkaline batteries are those little batteries that you can purchase in the grocery store that you use for flashlights, clocks, your calculator, etc. The cathode of this battery is manganese dioxide. Okay, and then anode of this battery is zinc and potassium hydroxide solution. And this is why from this the name alkaline battery came from. Potassium hydroxide is a base. It's considered as alkaline substance, and that's why we typically call these type of batteries alkaline batteries. And nickel, cadmium, nickel, metal hydride batteries were once commonly used because they were lightweight, rechargeable, provide higher electrical power. So these were used to be commonly used for portable electric devices that require higher power. But due to this cadmium being toxic, okay, the use of cadmium has significantly reduced in several years. Okay, and so the cadmium is replaced by this metal hydride. Okay, and so the nickel metal hydride batteries are similar to those little alkaline batteries, okay, that you use a lot in daily life, but these are rechargeable and more environmentally friendly than nickel cadmium batteries. Okay. Lastly, lithium-ion batteries. Lithium-ion batteries are getting a lot more attention these days. So, for its greater rechargeability, being lightweight, produce a lot more voltage compared to nickel-based batteries. Okay, so the lithium-ion batteries are commonly used for your cell phones, tablets, laptop computers, and even electric cars. Okay. And this is how your lead acid battery in gasoline car looks like. There are lead, and lead dioxide alternating, submerged in sulfuric acid. So here, each battery, this is each set of battery. I mean, this is the entire battery typically contains 6 voltaic cells. So each these are the each voltaic cells. Okay, these each produce 2 volts. So you have 1, 2, 3, 4, 5, 6 cells. So the total battery produces about 12 volts of electrical current. The right diagram is a sectional diagram of your alkaline battery where anode has zinc plus potassium hydroxide, cathode has manganese dioxide. Here's a diagram for lithium-ion battery. The anode has graphite. Do you see these graphites? These are nonpolar hydrocarbons. Cathode has lithium cobalt oxide. Okay, so do you see this lithium positive ions? These lithium positive ions can freely move through the electrolyte, okay? This is almost like a salt bridge, okay? These lithium ions can move through here or move from cathode to anode. When battery needs to produce electricity, when the electron has to go from here to here, lithium will migrate into cathode, so electrons can start to transfer to produce electricity. When battery needs to be recharged, lithium positive ion will migrate back into the anode, okay? And the battery is going to get recharged. There's another system utilizes voltaic cells, which are called fuel cells. So these are technically not batteries because they are not self-contained systems. So you need to continuously provide fuel to generate electricity through redox reaction. You need to continuously fuel these cells in order to produce electricity. Okay, so how it works is that when a fuel is burnt, the energy created can be converted to electrical energy, but a maximum of only 40% of the energy from combustion is converted to electricity in this manner. So, and the rest is mostly lost as heat. Here's a diagram of one of the fuel cells operated through hydrogen, which is called hydrogen fuel cells. So this fuel cell utilizes hydrogen gas and oxygen gas to produce water. And this cell can generate electricity twice as efficient as combustion engine. So why is it called fuel cell? Because fuel has to be continuously provided, right? So what's the fuel here? The fuel here is hydrogen gas. Hydrogen gas has to be continuously provided into the cell in order for this cell to operate and produce electricity. Okay. As for the oxygen, oxygen in the air is used, so you don't have to continuously provide oxygen. The anode side of the hydrogen fuel cell has hydrogen gas being oxidized to form proton. Okay, hydrogen gas is oxidized to form proton and then releases electron. The electron is going to pass to the cathode. At the cathode side of the reaction is oxygen is going to react with the proton, okay, and then produce water. So where did the oxygen got proton? The proton, the hydrogen after losing electron, it will generate a lot of protons. Those protons will slowly migrate into the cell that has oxygen, okay, and then with the help of the electrons that are passed through, hydrogen, proton, and oxygen plus electron will produce water. So that's that for hydrogen fuel cell. Next up, we will be learning about some undesirable redox reactions. So redox reaction can provide electrical power and be useful, but there are cases where redox reaction is unwanted, okay? For example, corrosion of metals. We don't want metal corrosions or metal rusting. So what happens during metal corrosions? The diagram here is clearly showing the chemical reactions occur during iron corrosion or iron rusting, okay, due to water and presence of water and oxygen. So as in the voltaic cell, there is a region where electron starts to migrate and where electron arrives, okay? So although this is definitely not a voltaic cell, I will still refer those regions as anodes and cathodes, okay? Anodes is the region where electron leaves, cathodes is where electron arrives, okay? So in this anode, okay, the anode side, what happens is that iron gets oxidized and loses electrons. It loses electrons. Okay, these electrons spontaneously move to where oxygen is and water is, and then generate water or hydroxide. Okay, the Fe2 plus, the product of the oxidation of initial iron metal, this product is going to become further oxidized under the presence of water and oxygen generating iron, generating iron 3 oxide. This has bronze color known as rust. Okay, so this is what happens during the iron corrosion, iron rust, rusting process. So, in order to prevent iron rusting, cathodic protection is commonly used. This is also called sacrificial anode. Okay, a way to apply cathodic protection is to prevent corrosion is coating iron with a thin layer of zinc. Okay, coating iron with a thin layer of zinc because zinc has lower because zinc has lower reduction potential compared to iron. When there are zinc and iron together, which one will get oxidized first? Of course, zinc is going to get oxidized first compared to iron due to zinc having lower reduction potential. So therefore, zinc is a sacrificial anode and iron is acting as a cathode. Iron is protected and we call it cathodic. We call this method to protect iron we call it cathodic protection. We're protecting the cathode using anode by sacrificing the anode. Okay. Another example is protecting. Another example of preventing corrosion is protecting the underground iron pipes. Okay, to prevent underground iron pipe rusting, another metal easier to become oxidized compared to iron is used. So in this case, instead of zinc, magnesium is used. Okay, magnesium also has lower reduction potential compared to iron. So when you have magnesium and iron placed together, there's a competition for oxidation, but magnesium will get oxidized first because it has lower reduction potential compared to iron. Okay, so during this process, magnesium is placed near the pipe connected by a metal wire. Okay, and then because magnesium has lower reduction potential compared to iron, magnesium will become oxidized first, acting as a sacrificial anode. Okay, so iron is acting as a cathode. It's protected. Okay, magnesium and zinc is acting as a sacrificial anode, becoming oxidized instead of iron. Okay, the last topic that we will cover in this chapter is electrolysis. So far we've looked at spontaneous reactions that generate electricity, produce electricity. But electrolysis is actually opposite of that. So electrolysis is a process where we actually use electricity to make non-spontaneous reactions to occur. Okay. So while voltaic cells, you use spontaneous reactions to create electricity, electrolysis is actually using electricity, using battery power to make the non-spontaneous reaction to occur, force these non-spontaneous reactions to occur. Okay, so any reactions that do not want to occur spontaneously in the nature, we make it happen. We force it to happen by using electricity, and that is called electrolysis. Electrolysis. Okay, for example, sodium chloride Sodium chloride would not want to be separated into sodium and chloride. This is a non-spontaneous reaction. Okay, if you okay, so if we place a battery, if we place a molten sodium chloride, okay, and then if we place a battery to produce an electric charge, we can actually use this electric from the battery to force the separation of sodium and chloride. We can actually force the separation and produce sodium and chlorine gas. Okay, so here's what happens in the anode side of the battery. Okay, so sodium chloride in the molten form will exist as chloride ion and sodium ion. Okay, so here's what happens at the anode. Chloride ion from sodium chloride does not naturally want to lose any electron. However, the positive charge of the battery, okay, the positive voltage of the battery will pull the electrons in. Okay, it will force the chloride to lose electrons that it does not want to lose. It's a sad process. It's forced to lose its electrons. Okay, so then these electrons will pass to the cathode side. So, and on the cathode side, here's what happens. What happens is that the negative side of the battery will push the electron out and force the sodium ion to gain electrons. Although sodium positive ion does not want to gain any electrons. But too bad, it is forced to gain these electrons, has to gain electrons. So so that's how the electrolysis occurs in this cell. Okay, so anything that does not want to lose electron, it is forced to lose electron through this positive voltage of the battery, and then whatever it does not want to gain electron, it's forced to gain electron due to the negative side of the battery, negative portion of the battery, pushing the electron to this cathode side. Okay, and now you have generated sodium and chlorine gas. You have successfully separate these, make this non-spontaneous reactions to occur. The diagram on the right is another example of the electrolysis process where steel object is coated with nickel metal. Okay, so coating something with metal is called plating. Okay, that's called coating something with metal. It's called plating. And since we're using electricity to deposit a coat of metal onto a the steel object, we call this process electroplating. Okay, so this is how you use electrolysis to perform the electroplating on the steel object. Okay, so during this process, what happens is that this is a nickel metal, okay, just solid nickel metal, no charge, nickel metal that does not want to lose electrons. It's forced to lose electrons because of this, the battery, okay. It's forced to lose electrons, okay, because electrons are stolen by this positive voltage of the battery, okay, and these stolen electrons are transferred to the other side, the cathode side, and transferred to the steel object. Okay, after having its electrons stolen, nickel solid is now going to become nickel 2 positive, okay, and it will float around this system. Okay, and then it will migrate into this steel object. The cathode side receive the electrons, and along with when the nickel 2 positive ion migrates onto here, along with these electrons, now the nickel metal is deposited onto the steel object. Okay, so nickel 2 plus positive will receive this electron and will get deposited as a nickel solid on top of this steel object, coating this entire steel object with nickel metal solid. Okay, so this is how electrolysis is used in the electroplating. So electrolysis is a process where we use electricity to make non-spontaneous reaction to occur. Any reactions that do not want to occur spontaneously in the nature, we make it happen. We force it to happen by how? By using electricity. Okay, and that is electrolysis. All right, we will now do some math problems related to the electrolysis. Since the amount of electron flow during electrolysis, this amount of electron transfer during the electrolysis process is very important in the amount of substance being produced during the electrolysis. Okay, so depending upon the number of electrons transferred, the amount of nickel solid gets deposited here, the amount of chlorine produced, the amount of sodium produced, it really depends on how much electrons have been transferred, how many electrons have been transferred from the anode to cathode. Okay, so since the amount of electron or number of electron, this is the key part for the electrolysis. Since the amount of electron flow during the electrolysis is important in the amount of substance being produced at the end, we will learn about a unit called ampere, which measures the rate of electron flow or current. Okay, so while electric charge is measured in coulombs, electric current is measured in ampere. Okay, the relationship between coulomb and ampere are as follow. So 1 ampere is basically coulomb per second. Okay, or 1 coulomb is basically 1 ampere is basically ampere times second. Okay, so that's the relationship. These two units are, the charge and current units are related. Okay, so Q is charge, I is for electric current, and this is how units are related. So common electrolysis math problems will ask you to find the final amount of substance being oxidized or reduced during the electrolysis process. So in order to find this information, you can utilize this map. If the electrolytic cell has charge applied or current applied, you can use that information to find the number of moles of electrons transferred. How? Charge on 1 electron is 96485 coulomb. So let's say, for example, you have charge of 30,000 coulomb applied. Then you can figure out how many electrons are transferred from the anode to cathode, right? 1 electron requires 96485 coulomb of charge. Okay, if you have 30,000 coulomb of charge applied, you can reverse find out how many moles of electrons are transferred. I'm sorry, this is 1 mole of electron. Okay. Okay, so if 1 mole of electron require this much charge, if you have this much charge applied to your electrolytic cell, then you can find how many mole of electrons have been able to be transferred from anode to cathode. So if you have number of moles of electrons if you have successfully found the number of moles of electrons transferred during this process, you can find the mole of substance being oxidized and reduced. Okay, and then using this mole information, you can find the mass of the substance oxidized or reduced using the molecular weight in the periodic table. Let's try a sample exercise. You will get a better idea. So this is an electrolytic cell. Calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum trichloride if the electrical current is 10 ampere. Okay, so we are told that aluminum trichloride is electrolyzed to form aluminum. Okay, and the question is asking how much aluminum metal was produced during this process. The question also gave us information that the battery is supplying 10 amperes of electric current for 1 hour. Okay, so we're going to step by step try to find out how much aluminum is generated during this electrolysis process. Okay, so the first thing we need to do is some unit conversion. Since we're given the electric current unit as ampere, we're going to convert it into coulomb. Okay. By the way, 1 hour is going to be 3600 second. Okay, so 10 ampere into coulomb. 10 ampere is going to be 10 coulomb per second times 3600 second. That equals to 3.6 times 10 to the 4 coulomb. Okay, so we basically did the unit conversion from ampere to coulomb. Okay, so now that we know that this much of current is applied in this electrolytic cell, okay, so we should be able to use this current information to calculate the number of moles of electrons that passed into the cell. Okay, so since we know that 1 mole of electron requires 96485 coulomb of charge, we have 3.60 times 10 to the 4 coulomb. How many mole of electron has been transferred? We will take 3.60 times 10 to the 4 coulomb times 1 mole of electron divided by 96485 coulomb. That equals to 0.373 mole of electron. This tells us that number of mole of electrons transfer from anode to cathode within the electrolytic cell. So now that we know that this amount of electron has been charged, let's take a look at the reduction half reaction to produce the aluminum. Okay, so if you're going from aluminum trichloride to aluminum metal, the oxidation number changes from +3 to 0. Okay, this tells us that in order to produce 1 mole of aluminum, 3 electrons must be gained. Okay, or in other words, 3 electrons would produce 1 mole of aluminum. Okay, so we know that 3 electron transfer will produce 1 mole of aluminum. We have 0.373 mole We have 0.373 mole of electron transfer during this process. So how many mole of aluminum were we able to get? Okay, so then we take 0.373 mole of electrons, okay, times 1 mole of aluminum divided by 3 mole of electrons, okay, that gives us that gives us 0.124 mole of aluminum. Okay, this tells us that when this amount of electrons were transferred within the electrolytic cell, this mole amount of aluminum has been produced. Were able to be produced. I'm going to write that down. Okay, this is the amount of aluminum that was able to be produced from transferring of 0.373 mole of electrons. Okay, now that we have mole information, can you find mass? You just have to go to the periodic table, find the molecular weight of aluminum, multiply number of mole to the molecular weight, you will get the exact mass, the exact amount of aluminum that you were able to obtain through this electrolysis process. Okay, so the mass of aluminum generated is basically 0.124 mole times molecular weight of aluminum is 27.0 gram per mole. That gives you 30.36 grams of aluminum metal generated through this electrolysis process. Okay. All right, anybody have question on this slide? No? All right, so I wanted to go over the voltaic cells again, but before I go over the specific part that I would like to go over, is there does any students have questions on specific topics for this chapter? Is there any part that you guys want me to go over specifically? Okay. All right, so let's go over the voltaic cells one more time. Okay, so this is voltaic cell. Again, this is what happens within the battery, right? So this is how the detail regarding the chemical reactions occurring within the voltaic cell. So the beaker on the left contains zinc. The beaker on the left contains zinc sulfate solution. Okay, and the beaker on the if it's in the solution, aqueous solution, it will be in a dissolved form. So you have zinc 2 plus metal, zinc 2 plus ion and sulfate ion floating around in this beaker. The right side of the beaker has copper sulfate solution. Okay, so you have copper 2 plus and then sulfate floating around. Okay, so and another thing is that this beaker on the left, it has zinc metal, a piece of zinc metal stick into the aqueous solution. The beaker on the right also has piece of copper metal submerged into this aqueous solution. Okay, these two pieces of metals are connected by wire. Okay, connected by wire, metal wire. Then the electrons just spontaneously start to move due to the spontaneous redox reaction. And by now we know why, right? Because copper has more positive reduction potential. Copper is more greedy for electron. It's natural instinct. Because of that more positive reduction potential, copper will try to steal electron from the zinc spontaneously. Okay, so the electrons spontaneously move from this side to the zinc side to the copper side. These moving of electrons generate electricity in the voltaic cell. So if you stick a light bulb in here, it will light up. Among 4 substances contained in 4 beakers, beaker here you have zinc solid, you have zinc 2 plus. On the right you have copper and copper 2 plus. Among 4 substances, because copper 2 plus is more greedier for electrons, when zinc and copper 2 plus fight for electrons, copper 2 plus wins the electron war, copper 2 plus will steal the electron from zinc metal. So electrons transfer from zinc metal will arrive at the copper side, and copper 2 plus will stick onto this copper metal, try to receive the electron. And now this copper 2 plus ion gained 2 electrons, it becomes copper solid. It will become deposit onto this copper metal. Okay, so if this process continuously go on, what will happen is that the copper metal will slowly gain its mass, because copper 2 plus deposit onto here, receive 2 electrons and become copper. So more and more copper metal is going to be generated. What happens on the zinc side? The zinc, after losing 2 electrons, it will become zinc 2 positive, and because ions cannot be part of the metal solid, this zinc 2 plus, now in ionic form, it will come out of this metal, escape the metal, and then it will get dissolved into this aqueous solution. Okay, so as time goes by, what happens is the zinc metal is going to lose its mass, okay, because more and more zinc solid is becoming zinc 2 plus, and then more and more copper 2 plus is becoming copper, and this will gain its mass. Okay, so zinc metal will lose its mass, copper is going to gain its mass. So the site, this is zinc losing electron is called oxidation. Okay, oxidation always occurs at the anode. Copper 2 plus gaining electron is reduction process. Reduction always occurs at the cathode. The electron will always flow from the anode to cathode. Okay, so oxidation will lose, the oxidation reaction occurs at the anode. We'll have electron lost. That electron will pass through this, follow this wire. It will arrive at the cathode at the reduction site. This half cell,
For the exam, will we have to figure out what is on the salt fridge, or will that be given?
So salt bridge can be anything, right? So you can have sodium sulfate, sodium nitrate. It doesn't really matter. Okay, so I'm not going to ask you what salt bridge do you need to have, but what you need to know is the purpose of the salt bridge, which I'm going to explain again one more time for you guys right now.
Okay, thank you.
So yeah, the left side of the beaker is also called oxidation half cell, or the right side of the beaker is called reduction half cell. Okay, because reduction happens here, oxidation happens here. So, purpose of salt bridge. The bottom line is that purpose of salt bridge is to neutralize any built up ions in both beakers. If you look at the left beaker, due to this continuous oxidation, more and more zinc 2+ is going to get built up. In that case, sodium, the ions in the salt bridge is going to provide a little bit of help. Okay, so in order to neutralize this too much built up of cation, the anion in the salt bridge is going to slowly migrate to this side. It will come out of the salt bridge and it will try to neutralize any zinc 2+ getting built up in this oxidation half cell. If you look at the right side of the beaker, due to the continuous reduction, more and more sulfate is going to get be left over. Okay, so remember you initially had copper 2+ and sulfate. Okay, but since more and more copper 2+ is being transferring into copper metal, a lot of the sulfate, the anion, is going to be left over, floating around in the system. So then the cation of the salt bridge is now going to slowly migrate to here, escape the salt bridge, and then try to neutralize any sulfate that is being built up. Okay, so easy way to remember, the anion of salt bridge will migrate to anode. The cation of the salt bridge is going to migrate to the cathode. That's the easy way to remember. Okay. All right, so that's that for voltaic cell, and then so the idea is pretty similar for all other voltaic cells. Sometimes the salt bridge is instead of U, okay, sometimes it's just like a barrier. Okay, that's totally fine as long as the ions can migrate. The ions in the salt bridge can migrate to neutralize. Okay, it doesn't have to be U shape. Okay, it can be a layer of sponge or something like that. Okay, so that's that, and then very important concept, standard cell potential. Okay, so the standard reduction potential here, this table, specifically showing the potential of this substance to become reduced. The potential of this substance to become reduced. This potential of this substance to become reduced. The potential of these materials to gain electron. How likely these materials, these substances, are going to gain electrons. Okay, so the more positive value, the higher reduction potential. The more positive this reduction potential value, that tells us that this substance is going to be very willing to, it will love to gain electrons. Okay, so more positive reduction potential value tells you more likelihood of a substance to gain electrons, to become reduced. Okay, so if you create a voltaic cell between copper and zinc, which one has the higher reduction potential? Copper has higher reduction potential. Copper 2 plus has higher reduction potential. That tells us that because copper 2 plus has higher reduction potential, when you create a voltaic cell using these two substances, the electron will spontaneously flow from zinc side to the wait. Why is it written as R? Oh. I did not notice that. Okay.
Pepper,
Yeah, I'm
I
so sorry.
actually had a question about the E naught.
Mhm.
So you know when we're trying to figure out the E naught of two half equations, so we have to use this chart.
Yeah, just give me 1 second. So
Okay.
I don't know why it's showing as R, but can you guys change it to arrow? I'm sorry. I think there was like a technical error when I converted this file to PDF. Okay, so make sure you change that to arrow. Oh, okay. All right. What's your question again?
So when we're trying to figure out the E naught when we have two half equations,
So E naught, what? Reduction potential or standard cell potential? So you, which one are you talking about?
I think it's a standard cell potential. Yes, it's that one.
Here, okay, E cell, okay?
So when we have two half cells and we're trying to figure this equation out, we would use the standard reduction potentials chart to figure out the values.
Correct.
Okay, so what if one of our equations is flipped? One of the half equations is flipped. Would we change the value of the reduction potentials? So for example, if you look at copper's reduction potential,
Okay, so I know what you're talking about now.
okay,
So let's say this is oxidation, right?
right.
This is oxidation, and are you asking me if you want to find reduction potential of this equation, right?
Mm-hmm, correct.
Yeah. So if you say flip the equation, that's kind of incorrect. Okay. That is a okay way to put it if that makes yourself easy to understand. But the correct way to say is that you need to find reduction potential of zinc 2 plus. Okay. So how likelihood zinc 2 plus is going to gain electron, that is going to be the reduction potential. So yes, you are flipping the equation, but technically you're not flipping the equation. You are finding a potential that zinc 2 plus is going, the likelihood that zinc 2 plus is going to gain 2 electrons. Does that make sense?
Yes.
Mm-hmm.
So would that value be changed instead of being a negative? Would it be a positive now?
No, this is oxidation potential, right? Do you see oxidation potential on this table? No, this table only has reduction potential. So you're looking at the reduction potential only. So you're basically, there's a electron war between copper 2 plus versus zinc 2 plus. Who has stronger pull for electron? You are finding that. Does that make sense?
It does.
Yeah.
I was
So
just confused.
yeah. So between zinc 2 plus and copper 2 plus, if you look at the table over here, who has stronger, between copper 2 plus and zinc 2 plus, who has stronger pull for electron?
Copper.
Copper. So that's why copper is going to be at the cathode side, the reduction side. It will receive the electrons. Does that make sense?
Okay, so we never change the from a negative to a positive or vice versa.
No, you will use this value as it is. This is a reduction potential.
Okay, even if the equation is flipped, like I say.
Equation flipped means different equation. equation, if the equation is flipped, that's referring to oxidation reaction, not reduction reaction.
Okay, that makes sense.
That makes sense? Okay. Yeah. All right, we're out of time, but does anybody else have any other questions?
I had another question regarding the homework.
Uh-huh.
Number 21 and 23 look a little different than what we were taught.
Let me see. Okay, give me some time. I need it takes quite a bit of time for me to open the Macmillan Learning. So
Yeah, that's okay.
what is it about? Chapter,
Um,
what chapter? Chapter 20?
Yeah, chapter 20, numbers 21 and 23.
Number 21 and 23. Okay, let me take a look. All right, 22. Chapter 20. Is it conceptual or regular homework?
Regular homework.
Regular homework. Oh, okay. Um, all right. So this the double vertical line basically tells you the salt bridge. Okay. So in one half cell you have copper and copper 2 plus, and the other half cell you have silver positive, and then silver solid.
Okay, that makes
Uh-huh.
sense.
Yeah.
Okay, thank you.
Uh-huh. Yeah, I forgot to explain this to you guys. And then you had a question about question 23 as well?
Well, 23 is the same. I was
Same,
just
yeah.
confused on the order.
This vertical line, it's based the two how should I say it? The two vertical lines side by side in the middle, the two lines in the middle, that's
Yeah.
basically salt bridge.
Okay,
Yeah, this is a common way to express a voltaic cell.
okay, thank you.